but it still deals with kinematics, right? We went through frames. Where do you assign the frames? We talk about forward kinematics, inverse kinematics, right? Forward kinematics is when you are given your joint angle, right? It can be joint angle for rotary joints. It will be joint length with prismatic joint, right? But this is going to input to the actuator. Unknown is if I have certain input to the actuator, what is the output and the effector, right? So this is what you want to find in forward kinematics. So it's a straightforward process of inputting the value. Inverse kinematics is the other way. You know that I want to go to this position or pose. When I say pose, it means position plus orientation. When I just say position, it is just XYZ. Right? Pose, there's a meaning to it. So I give you this N effector pose, and what you're supposed to find is what are the inputs should I do to the actuators, help me to reach that. Now this is the one that is a bit painful because you have to do a lot of reverse calculations. Okay. This is more of frame assignments. We talked about this 4x4 transformation matrix. Right, we talked about this 4x4 transformation matrix, where this 3x3 matrix here is your orientation matrix. This Px, Py, Pz is your location of your moved origin from your reference origin or your previous origin, frame, sorry. Right? So these are the two key things. And also remember, your bottom row is 0, 0, 0, 1. Why 1 over here? Why? Scaling, right? Because it's rigid structures, we can't stretch, we can't compress, so that's why it's 1. We don't have any scale to it. You can have a few types of motion, pure translation. That means there's just a movement by X, Y, Z. Right? You can have pure rotation, that means your origin of the two frames before and after are the same, just that they have moved a bit. Or you can have a combination, which is what you will mostly face. Okay? So again, if you have pure translation, remember this format, this is very important. When we go through the example today, you have to remember this kind of formats. It is pure translation, your rotation matrix will be identity matrix. That means that when your rotation matrix is identity matrix, there is no rotation. Right? You just need to put in these dx, dy, dz terms. Right? Okay, these are some examples that we went through. Okay, we also went through the basic rotation matrix when you rotate about x-axis only, y-axis only, and z-axis only. You will use these basic matrices or rotation matrices to form your overall transformation. Because sometimes you may have sequence of motion. Maybe move by x-axis first, then by y-axis, then z-axis. This information are known to you. You need to input it into the matrix. You need to pre-multiply, post-multiply. That part will be coming soon. Okay? You need to remember these matrices. It will not be given in any formulation. Okay? Okay. Yes, these are important part. If you always have a before and after transformation frame, right? And you will have successive transformations. You may not have just one, you may have 2, 3, 4, for example. If you are going to make your fixed frame as a reference for all subsequent motions, it should be pre-multiplied. Okay, we will go through this with an example to highlight this. Now, let's say I have this frame, my fixed frame, I have moved to another frame. This fixed frame is, the first motion will always be a reference to a fixed frame. I want no two ways about it. Now, after you move here, from here to another frame, if you are going to do this transformation with respect to the moved frame, not your ground earth frame, then you should do a post multiply. Okay, remember this. In the exams, the questions are they may tell you that, oh, you are moving about your n-axis, o-axis, a-axis. That means with respect to your moving frame. They say I'm moving with respect to your x-axis, y, z. This is with respect to your fixed frame. So I'm telling you some observational tips to identify what to do. Alright? Remember, XYZ is fixed when your moving frame is more of NOA. Right? Remember that sequence. XYZ more of equivalent is NOA. Okay, this was the thing that I went through in class. So if you have subsequent, you have motions, every motion of this A, B, and C are respect to your fixed frame. The gray axis. You should always do a frame multiply. See, 1, 2, 3, frame multiply the transformation. Once you get this transformation matrix, you have any position in your moving frame, you multiply the transformation matrix with that local coordinate and you will get your global coordinates. Now, this scenario is what I said, moving frame. So from U to A is straightforward, but from A to B, when you move to B, you are using A as a reference instead of frame U. So then you will do a post multiply. Post multiply is on your right. Okay. Some properties of a rotation matrix. If you ever need to find your inverse of your rotation matrix, it's just a transpose. Okay. You went through this as well. They may also ask you to find inverse of an entire 4x4 transformation matrix. Again, remember, you have two components in this transformation matrix, your rotation matrix and your position vector. Right? So for your rotation matrix part, it's just a straightforward transpose. But for this portion, your position vector, now instead of going from A to B, you're going to go from B to A. So that's why you have a negative sign. And because you want to make B as your global frame now, you will multiply your column vector with the transpose of the rotation matrix. Because you're doing an inverse, you're going backwards. Just take note of that. Okay, let's do some quick examples for this, and then I'll review again lecture 4, then we'll do another quick example. Okay, apparently I can't split this. It's okay, I will use, I'm sure you all have the question papers like similar in Moodle. Okay? So I may not go through all the questions, but some of them are similar, but the practical questions of how you go about answering them is something I want to go through with you. Okay, question 1 is quite straightforward. 2.1. They give you a vector P. If I ask you to do a scaling, of this vector, what does it mean? What would you do? Times 2, straightforward, okay? If I want, okay, so let's say 2.1 A. Now you are given P, which is, you can put it in a vector format, column vector format. if I say scale factor of 2, what it just means is P will become now 2 times 3, 5, and 2. Okay, rather straightforward. Right, so there will be 6, 10, and 4. Okay. Now, if I want to describe this as a unit vector, what do I do? Divide by the magnitude. Okay. Good. Some of you are still familiar with it. Okay. So usually we use a head or a bar. Okay. Either one is okay. So what you do is this. There is this magnitude. I just call it magnitude of B first. Then there will be 3, 5, and 2. How do you find this magnitude of B? How do you find the magnitude of a vector? Basic, square all the elements, add them up, then square root. It will be 3 squared plus 5 squared plus 2 squared, square root. Okay, this is your magnitude. Whatever answer you get, you put it in your magnitude. Okay. So far, okay? You need to know all these basics. If you don't know all these basics, you better go and brush up. You will need to use a lot of this for your subsequent questions that comes out in the exam. So just brush up these simple basics. Okay, 2.2. Now I'm given a Q unit is 0.371, 0.557, and QZ. Okay, ignore the 0 first, don't bother about the 0. Okay. What does Q unit mean? Magnitude of Q unit will be equals to 1. And what is the magnitude of Q unit? 371 squared plus 0.557 squared plus QZ squared. Square root this. Okay, I want you to practice the square root. I know it doesn't. You can bring over the square root. Square of 1 is still 1. But I want you to practice this so that you know that magnitude is actually you do a square root. Okay, so from this you can find your QZ. But remember your final answer, remember to square root it because this QZ is a square. So I mean for those who want to just double check, your QZ should be 0.743. Just to verify your answer. Okay, 2.7. 2.7 tells you this. I have this point P234 attached to a rotating frame. Now, when I read that, I will tell myself that this point P is respect to a moving or fixed frame. Moving, because of the word rotating frame. Okay. Now, this frame rotates 90 degrees about the x-axis of the reference frame. That means, whenever you see x, y, z again, okay, you should take note that they are referring to your fixed global frame. Right? But then this is just straightforward. It's not asking you to do any transformation yet. Right? But it's telling you I'm rotating 90 degrees about x-axis. If I'm going to rotate about the x-axis, I will rotate it this way. I will say x, then 90 degrees. Okay. Then you need to remember your basic rotation matrix. Remember this is x, so your 1 will be here, 0, 0, 0, 0. Okay, remember this. This is the first step that you do. Okay. After that, there will be some cosine theta, sine theta. You know, the diagonals will be sine. You need to remember this sequence. And remember the negative sign over here. So your theta will be equal to 90 degrees. You input in, you'll get some answer. Okay. This is what the question is telling you. Now the other portion, the real question comes in, is find the coordinates of the point relative to the reference frame after the rotation. So they have given you the position of the point P with respect to the moving frame, right? That is 2, 3, and 4. Now they want you to, now you have done some rotation to this frame, they want you to find the global position. Right? Now let's say, let's put it this way, if you are driving a car, with respect to the car, you are always on the driver's seat. But with respect to your home, maybe if you are parking near your home, you are nearby, maybe it's half of 500 meters, for example. Maybe if you go to school, maybe it becomes 10 feet. Right? This is what it means. So I want to find out the absolute location of you with respect to your reference, which is your home, for example. Same thing. This is what it's asking you. Okay? I have a local point, I want to know the global coefficient. So that's why you need to know your rotation matrix first. So your global coefficient will be Px, Py, Pz. Right, this is 3 by 1. Your R will be x, 90 degrees, 3 by 1. 3. Okay, verify. This will be your P. Okay, I will use this notation, P, N, P, O, P, A. Right, this just basically refers to your 2, 3, 4. This is 3 by 1. Sometimes you may confuse, for this kind of column vector, should I post multiply, pre multiply? There's only one thing you should do, post multiply. Okay, look at this. Okay, this should match. These two should match. Okay, so that's what asking you. Find the coordinates of the global position. I have a local position, find the global position. That's it. Then once you find this answer, this is your final answer. You want to verify 2 minus 4 and 3. Again, if you can get a hold of the book, these are all there. I just want to go through these examples. Okay. Okay, this is where there's a sequence of actions coming along. Now you assume that you have this same point, not the same point, it's a different point by 7, 3, 1. Then you are attached to frame NOA. Whenever they say frame NOA, once you see this NOA, it refers to the moving frame. Okay, they say maybe XYZ, it refers to the fixed global frame. Okay? Are you able to see? Clear, right? Okay. Now you have this point to this moving frame. It goes through these three sets of sequence. First, you have rotation of 90 degrees about the z-axis, which is a fixed frame. Then you have a translation of 4 minus 3, 7. 4 refers to the x component, minus 3 is the y, 7 is the z component, z-axis. Okay. Then again you have a rotation of 90 degrees about the y-axis. Okay, y-axis is the respect to the fixed or moving. Fixed, good. Okay, so you can put it this way. You have three sequences. 1, 2, 3. First, you will do a rotation about your z-axis by 90 degrees. Second one, you will do a translation by 4 minus 3, 7. Third one, you will do a rotation about your y-axis by okay, this is the first step. Second step is to find all your transformation matrices. Right? So for this one, the T1 is put it in. So remember to go and find out this exact rotation matrices. Okay, because it's just pure translation, right? What will the position vector be? If your two origins are coincident, what's the position vector between these two origins? 0, 0, 0, right? So 0, 0, 0. Remember your bottom is always 0, 0, 0, 1. Again, I remember this is 3 by 3 matrix. So this is how your transformation matrix one will look like. Exam questions will ask you this. Some sequence happening. How do you form up your 4 by 4 transformation matrix from the basic matrices? Okay? This is T1. When you go to your second step, if you have a pure translation, the rotation matrix is 0. Identity matrix. Okay, identity matrix is 1, 0, 0, 0, 1, 0, 0, 0, 1. This is identity matrix. But you are translating by 4 minus 3, 7. Okay, remember below 0, 0, 0, 1. Remember the last row is always very straightforward. If you really supposed to do this, if you need some spare marks, the least you can do is write the 0, 0, 0, 1. You'll get something. I will guarantee I'll give you something. But I don't know how many marks is there. But better than nothing. Okay? So we work smart. Okay? Okay, third one. Transformation matrix of 3. Now you will do a rotation about y 90 degrees. Again, it's just pure rotation. 0, 0, 0, and the bottom is 0, 0, 0, 1. Okay. First step is make sure you identify these things. Second step, identify the details of this. So you need to remember how to, what is the form of a rotation about z, rotation about x, rotation about y. Okay? You need to know that format. Okay. If you look at these three steps, if you look at the first step is always, okay, what they want you to find is this thing. I have this sequence of motions, I have this local point. What is the location of this point after I've done all these three steps? Okay. So what you need to do first is find the overall or the total transformation matrix of steps 1, 2, 3. Okay. So you will know the first step is always T1, right? That has to be the first step. Now the second step and third step, this is the one you need to take note. Okay. So T2 is doing a translation, and usually it's about the fixed frame. So your pre or post multiply? Pre, yeah? T2 will come here. Then the third step is you rotate 90 degrees about the y-axis. Y-axis is the fixed axis. So you again pre or post? Pre multiply. Okay? You will input in all these matrices, you will find some overall matrix. Again, there will be something here, there will be something here. What's the bottom? Okay? So this is still not the end of the question. This is just still the second last step. So you want to find your global points, x, y, and z. Okay? It will be this T total that you found times your Pn, Po, Pa. What is this value from your question?
4.
What's the value of this vector?
4 minus 3,
7, 3, 1. Okay? Your Pn is 7, Po is 3, Pa is 1. Okay, you solve this, then you reach your final. So far, okay? Right, so it's quite methodological. You just need to read the question, then understand respect to the fixed frame, moving frame, find your individual transformation matrices, and then you either pre-multiply, post-multiply, depending on what the question asks you. Okay? 2.10 is something similar, but in respect to your moving frame. You see, they are quite clear. Rotation for 2.1, rotation about A-axis. Translation along NOA axis. Then for step 3, rotation about O-axis. So it's all of these will be post multiply. Remember. Okay. Okay, you guys can try out 2.10, 2.11. 2.11 on your own as well. Okay, I'll go through. Okay, for 2.11, don't worry about. Okay, write the equation that describes the motion. We are basically talking about transformation matrix. That's all. Right? You just find for each step that you do, find the transformation matrix, and then what's the final location of point P respect to your reference frame. So what you've done, the last step of post multiplying your local position vector to get the global position vector. Okay, we'll go through 2.12. Some sequence to be done. Okay, 2.12 states that a frame F was rotated about the y-axis by 90 degrees, followed by rotation about the o-axis by 30 degrees, followed by translation of 5 units along n-axis, finally a translation of 4 units along x-axis. Find the total transformation matrix. So step 1, what is it? Rotation by y-axis by 90 degrees. Right? Second step, rotation by o-axis by 30 degrees. Third step is translation by 5 units along the n-axis. What does that mean? They are just saying that it only moves 5 units by the n axis. The other axis are 0, 0. Okay. So n axis, I remember, is a NOA, something like this. So it's 5, 0, 0. Okay. Fourth step is translation of 4 units along x-axis. So x, y, and z will be 4, 0, 0. Okay. Again, for rotation matrices, pure rotation, there won't be any position vector. I won't go through that again. For translation, your rotation matrix is identity matrix. Okay, remember that, pure translation. So a lot of things are already determined for you. Once you know these things, then you just put it in, you get a mark. You are getting that, right? Find the total transformation matrix. So T total A. Let's say you have a T1 here. From here you get a T2, T3, T4. So these will be all 4x4 matrices. First step is always E1, right? You have to start somewhere. So I'll just put it in the center first. If I look at my second step, I'm doing with respect to the moving frame. So I will post multiply. That means T2 will be here. Okay. Agree so far? Third step, I'm doing a translation about my NOA axis, which is my moving frame. Good, moving frame. So again, if it's the moving frame, I will force multiply. Then the last step, I will do a translation by 4 units along x-axis. X-axis is fixed, so 3. Okay, this is the sequence we should do systematically. Okay, you multiply them together, you'll get some answer. Clear? If I need to find a matrix representing rotation or inverse of rotation, what do I do? What will I do? If I need to find the inverse of a rotation matrix, we will just transpose. We will just do a transpose of that rotation matrix. So straightforward. 2.14. I have given you this particular 4x4 transformation matrix. Okay, this is what I have given you in the example. Remember, this portion is my R matrix. This portion is my position vector. If I want you to find the inverse of this, what will you do? What will happen to my R? R transpose, right? R inverse or R transpose is the same thing. Okay? Again, put the 0, 0, 0, 1 first. What happens to this portion? This portion is, first of all, there will be negative, right? Because it's going in the opposite direction of the two frames. Then you will do a RT, then you multiply with this P. right? This entire value will go in here. This will be a 3 by 1 column vector. It is 3 by 3. Okay, this is how you find the inverse. Okay, so far, method, just method, just need to practice a bit more. Once you know the method, it shouldn't be a major issue. The most, I would say, the challenging part is just multiplying the figures. That's where we tend to make error mistakes. But if you have something there, I can give you some marks. Okay, don't leave it as a blank page. Yeah. Okay. This is the end of what? It is first lecture 3 exercise. Okay, and then after that we move on to lecture 4. I know it seems a bit of a rush, but we had to get the fundamentals covered now so we can practice it. Okay, so lecture 4, what we talked about, we went into the nitty-gritty details of inverse kinematics. We looked at forward and inverse, but we separated into two. One sort of formulation just looked at position. Right? We had Cartesian, cylindrical, and spherical coordinates. How do you realize whether it's cylindrical, Cartesian, or spherical? Look at the joints. When you move these joints, what kind of workspace they form. Right? That is how you identify it. And then after that, we looked at two approaches for orientation. It's pure orientation. Just maybe about just rotation about the axis. So we had the row pitch yaw and the Euler angle. Right? Again, when you look at Cartesian, when you look at the workspace, it will form like a box. Then you roughly know. But then the other more important thing is take note of the joints. Cartesian robot will always have all prismatic. In the exam questions, they may give you a robot configuration. They may not even tell you whether Cartesian or cylindrical or spherical. How you determine it? Look at the joints. Look at the joint it has. If it's all three prismatic joints, it should be a Cartesian. Right? And for Cartesian, the forward and inverse is very straightforward. Whatever position you want to go to, that's the value you put into the actuator. That's what you get. If they give you Cartesian, wow, you should be very happy. It's just a straightforward answer. Don't need to do much calculation. Cylindrical, they would have one rotation and two prismatic. Now with this kind of joints, you will form a cylinder kind of a workspace. That is how you identify that this is a cylindrical robot with a cylindrical coordinate. Okay? And you should take note of this matrix. Okay? Remember, it's not just because there will be some sequence of motion, the robot has to do some motion. But in that motion, it has some undesirable effects when there's some rotation comes into it. So you need to unrotate or compensate this. Right? So once you compensate, you will get a form where your transformation matrix, your rotation matrix will be an identity matrix. And all you are left is a position vector, which is R cos alpha, R sin alpha, and L. These are the three parameters you need to find for a robot. You put it in the robot to go to that position that you want. Right? Remember I said position, because we are still talking about X, Y, Z, no orientation. The orientation should be the same as the global frame. Okay, that's why we have the unrotation part. Okay, so for this, when you are given an n effector point. Okay, I want to reach x, y, z this location. You are just supposed to solve these three equations. So your L is straightforward. This is the part which I will go through with you how to solve it. Okay. Again, spherical coordinates you will have is different again. Now you will have two rotation matrices, one perspective. So the workspace, when you look at it, is like a sphere. That's how you try to make quick references to what kind of robot it is. Right? You just look at when you're given exam paper or exam question, just look at the joints and just visually or your mind rotate each joint and see what kind of workspace you get. You need to scribble on the paper, go and help you visualize it. That will help you to quickly link up. Again, same thing. You do some motion, there are some undesirable effects where you need to unrotate or compensate back. Because in this motion, again, your transformation frame, we just want pure translation. We don't want any rotation. So we are doing compensation to remove all these rotations. So then again, you will get this final format. You need to take note of this format. When you are doing your inverse kinematics, your given x, y, z, you need to find your r, beta, and gamma. Okay, then these are for position. Then for orientation, we have two. Roll, pitch, yaw. Okay, this one you need to remember the sequence. For orientation, sequence is important. If you want to use the final solutions, these are the final solutions. Let's say we don't talk about exam when you are working, you are considering a robot. You want to use these final solutions. You have to move your robot in this sequence the same. Roll about A-axis, then pitch about O-axis, then yaw about N-axis. You have to follow this. Because it is based on this sequence that they get the solution. If you screw it up, maybe you want to happily go about O-axis first, then A, then N. Although you input in the actuator information, if you want to move here, maybe you might just because your sequence is wrong. Okay, these are the realities people don't realize. Think that everything I follow everything. What are you sure you follow everything correctly? There is a sequence, so I want to emphasize the sequence is very important. Okay. Again, this one I know is a bit of a pain, but again, they don't want to give any formulas. You have to take one, right? And in the questions, they may not even tell you if it's a Euler or Robichaud. How you identify whether it's Euler or Robichaud? Look at the symbols for the angle. Okay, Robichaud will have these symbols, your sine and AON. Right? They will give you this symbol for the angle. For Euler angles, they will give you this sine, theta, and another sine. Right? So when you see this, you should automatically distinguish whether you're supposed to use Euler or you're supposed to use Robichaud. Right? The symbol of the angle. Okay, so far, telling you some tips to be more observant and find out your answers faster. Again, this you need to follow the sequence. Rotate about A-axis, O-axis, and then again A-axis. So there is no such thing as you must move every axis. It's up to how you prescribe it. If you want to use some of the axis, go ahead, but you need to carry out 3 rotations. Come up with 3 rotations. This is a must. Right? And then there are a lot of methods, but we just share with you. Okay. Okay, let's do some exercise, so at least you have some idea. If not, you may think that I'm blabbering wrong. Okay. Yeah, before that, I just want to share with you this. Wow, very complicated. Wow. Yeah, just tell you simple thing to remember lah. Just remember this. C-A-S-E. That's all it is. In this quadrant, all your cosines are positive. In this quadrant, whatever angles you have, all will be positive. Sine, cosine, tangent. This is where all your sine angles will be positive. This is where all your tangent angles will be. So when you look at angles, it means these angles. These so-called principal angles. Okay. This is a bit more detailed form. If you don't have a calculator, you can use this to find some answers. So it's just some reference. So if you need to find cosine 90, then you can find answers. Okay, gradients. Okay, let's look at the question. Again, I emphasize again, these are all from the textbook. Okay, okay. 2.16 is designed to position the origin of the hand frame of a. Okay, the questions here are very kind, I'll tell you. But I will have another session with you sometime nearer to exam time. I'll go through some of the exam questions. Okay, you will know that they never tell you, or they seldom tell you. Okay, so at least now we take it as one step towards your final goal. At least you familiarize yourself with, okay, if I need to use Cartesian, what should I do? If I need to use limiter, what should I do? Right? Okay, so Cartesian, first thing you should take note that my transformation matrix will be I, Px, Py, Pz, 0, 0, 0, 1. And what the question is saying is, I want to go to this point called 3, 4, 7. I want to go to this point. Right? I just want to go to this point. All you need to do to find the inputs you need to put to your linear actuators. Right? Your linear actuators will take in these values, right? Just do a comparison between this and this. That's it. Your answer will be Px is 3, Py is 4, Ez is 7. So that's why I say if they give you Cartesian robots, you should be very happy. Quite fast. Okay. Okay, 2.17. 2.17 is, now we want to place the origin of the hand frame of a cylindrical robot. N347. Find the joint variables of the robot. What are the joint variables of this robot? How many angle and how many length information do you have for cylindrical? Okay, good. 2 translational information parameters and 1 rotational parameter. So if you look at your 4x4 transformation matrix, it will be I. Remember, unrotated. Okay, because we want to compensate the effects where there was some orientation to your frame. Okay, this will be R cosine alpha, R sine alpha, L, that is 0, 0, 0, 1. Again, I want to go to this position 3, 4, 7. What I will do is, I just have to compare between this and this. So for first instance, I know that L equals to 7. Okay, 1 mark. Okay. Now the tricky part is this one. Now you have R cosine alpha equals to 3. R sine alpha equals to 4. Okay. Remember, whenever you look at these equations, you need to find out what is your value of your cosine and your sine. Okay. Because your R can never be negative. Okay, you take note of that. So because you have this, so from this, right, R will always be positive. So if this is positive, to get a positive answer, that means your cosine alpha should be positive, sine alpha will be positive, right? They cannot be negative because negative multiplied by a positive number will result in a negative number. Okay, take note of that. This is the important part. This will tell you where your angle will lie. Where will my cosine be positive? Which quadrant? Let's say I have quadrant 1, 2, 3, and 4. 1 and 4, right? For cosine. Okay. Where will my sine alpha be positive? 1 and 2. So the only place where both of them can exist as positive values will be at quadrant 1. Right? So this is your angle that you will be looking at. For the angle, you should give an answer. Okay? Now, we know that there is another relationship for your tangent alpha is sine alpha over cosine alpha, right? But we know there is an R here. This is 4 over 3. Right? So the alpha is inverse 4 over 3, 53.1 units. Okay. You don't have to do anything because this is the alpha value. Sometimes if questions require you to find angles which are here, in this quadrant 3 you will need to do a 180 degrees plus alpha. If your question requires you to do it, but not for this question. This question is fine. Okay. Once you find this, you can plug in either one. Right? R equals to 3 over cosine alpha. You plug in your value, you should get something, whatever equals to 5. Okay? This is the reason for you to use that 4 quadrants. This is a bit straightforward. There are some instances where you have 2 sets of answers to deal with. Okay, so far? The trick or the tough part will be finding out or remembering that first transformation matrix, the T cylindrical, that form. That will be the tough part. Once you know that, once you can equate in the potential with this, this is how you will follow the solving process. Okay. Okay, 2.18. 2.18 is, I will just quickly go through 2.18 because, okay, this is also a T cylindrical question, right? But now instead I want to go to this position. Okay, I'm given this. So I want to go to this minus 2.394, 6.5789. I want to go to this point here. Basically, I'm just comparing this with this. I just want to go through this example because this is a scenario where my sine and cosine are both not positive. So how should I deal with it? How should I answer this? Okay. So straightforward, L equals to 9, right? Done. Okay. Now you have R cosine alpha equals to minus 2.394. R sine alpha equals to 6.578. By virtue of fact that R should be positive, that means my cosine alpha is negative. Right? Correct? Because of this negative sign. And again, for sine alpha, this will be positive because my overall answer, this is positive. Because positive and positive is positive. Okay, so the trick, now the important thing is where should my angle, this alpha lie. If I look at my cosine, okay, if my cosine is negative, where will which quadrants will my angle lie? 2 and 3. Okay, for positive sine will be 1 and 2. So the commonality will be at quadrant 2. Okay, now when you look at quadrant 2, you will find a principal angle. So when you do your tangent alpha, right? You get your alpha equals to some value, right? This is your alpha value. But the final answer you should give me is not this directly. If this is my zero reference line, right? This angle which I need to put in is this part from here to here. So let's say I call it alpha final will be 180 degrees minus alpha. The key idea is this: once you find the angle, if you want to verify on your own, once you find your answer, you put it back in. You should get the same. You put them back in these equations. You should get the same value. If your negative positive is not what it should be, that means your answer is not right. Okay, to verify. That's why we are doing this. You want to get the right angle to satisfy both of these equations. Okay, let's do one more before we call it a day. Okay, we look at 2.19. Now we want to place the origin of a hand of a spherical robot at 347. Okay, so T spherical, again this is what? Unrotated. R sine beta cosine alpha, R sine beta sine alpha, R cosine beta, then 0, 0, 0, 1. How to position it to 3, 4, 7. So I will compare these three terms with these three terms. That. Okay. So you will have r sine beta cosine alpha equals to 3. Right, your first equation. Second equation will be r sine beta sine gamma equals to 4. R cosine beta equals to 7. Okay. If you look at 1 and 2, you can't really tell what is my alpha and beta, where they should lie. My sine beta, sine alpha. Only thing that I can know is from my third equation. That because r should be positive, so my cosine beta is positive. That's the only thing I know. I don't know anything about sine beta. Because I don't know anything about sine beta, then it becomes a bit difficult for me to assess whether this which angle or where does beta lie at the moment. So I KIV that first. Okay. So I start with 1 and 2 first. So if you look at the commonality between these, you will get tangent gamma is right, you can cancel out these terms, but then you will get 4 over 3. If I look at my tangent gamma, it's a positive value, right? Correct? If it is positive, where should this lie? 1 and 3. Right? So whatever value you get, this is one value that you should look at. The other value is from here to here. This is 80 plus. Okay, this is where you need to take note. So end of the day, you will find this principal angle is 35.1 degrees, right? But you will need to use two values. One is 50, this value, and 180 plus 53.1. Then you start having two answers to work with now. Because there are two scenarios now, where your alpha, your gamma will be, tangent gamma will be positive. Okay. So with this, you can find what is your sine of gamma, some value here. You will have two values. Then cosine gamma, you get some value. Okay. Then your r sine beta, you can just use either equation 1 or 2. Right? You will get some values. Right? Now, why I can find these two is for me to help to find using one of these equations to find my beta. Okay. Okay, once I know this, then there will be, okay, if you look at the example, they will tell you 5 and minus 5, you get these answers. Right? And you know r cosine beta is positive. If these are both positive, where will they lie? Quadrant 1. If my sine is negative, my cosine is positive, where will it lie? Quadrant 4, right? Right? Sine is negative, but cosine is positive. Where will the quadrant be? This is the only place. Right? So this is to tell you, once you find your answer, my beta should be this value. Or when I find for this sequence, the answer should be minus beta. The negative sign should be there. Okay, so from this you will realize that your beta is 35.5. But for this answer, your beta should be negative 35.5. or 360 degrees minus 35.5. That answer also is also fine. I'll accept that. Okay, once you know your gamma, beta, then your R will be, you can find your R value. Okay, this is a bit tricky, you need to take note. Because you are comparing equations, you need to know which one is positive, negative, which answers. When you find the answer, you plug it back in, should give you the same answer. Okay, okay, thank you. We will end off today here, and then next week we'll continue with a bit of this.